Why doesn't the moon fall down?
Actually, the moon is always falling toward the Earth, but it's moving so fast that it will never hit. When we throw an object, like this tennis ball, gravity pulls it down towards the center of the Earth. Even the fastest moving tennis ball will eventually hit the ground. But as objects get farther away and start moving faster, things change. The moon is so far away and moves so fast that down is never in the same direction. Even though it's constantly falling, the moon never hits the Earth. Instead, it falls around the Earth in a continuous circular path. If the moon were moving a lot faster, it would escape Earth's gravity and fly off into space. If the moon were moving more slowly, gravity would pull it down to the Earth. This delicate balance of speed and gravity creates what we call an orbit, where a smaller body circles around the larger one continuously. The moon orbits around the Earth this way, just as Earth and the other planets orbit around the Sun. Most man-made satellites orbit the Earth. However, some are launched beyond the Earth's gravity so that they orbit the Sun instead. For Ask an Astronomer, I'm Doris Dow of the Sort of Science Center.
Now, we've already defined a force as a push or a pull, but Isaac Newton thought of a force as an interaction between two different objects. Our students are in the lab investigating this concept. Let's watch.
We used this exploder cart in the last lab. This time, we push in the spring to set the exploder and place the cart in the middle of the table. When the pin is tapped, the exploder is activated, but the cart doesn't move. Let's try again, but this time we'll place the exploder cart so that it touches another part of identical mass. When the pin is tapped, the carts move in opposite directions at the same speeds. This illustrates Newton's third law of motion.
Newton's third law of motion is also known as the law of interaction or action-reaction. For every action force, there is a reaction force of equal magnitude in the opposite direction.
The action and reaction were easy to see when the two carts pushed each other with equal force in opposite directions. But what about this example? What pushed the cart this time? If you said the wall did, you're right. The cart's exploder pushed backward on the wall, and the wall pushed the cart forward with the same force. The wall furnished the net force needed to make the cart accelerate. But why didn't the wall accelerate in the opposite direction? It did.
Did the wall really accelerate in the opposite direction as the car? The answer is yes. To explain, we'll have to go back to Newton's second law, F equals ma. If the forces exerted on the cart and the wall are the same, what about them is different? Tell your teacher. If you said that the masses of the cart and wall are different, you're right. The mass of the cart is small, so the cart's acceleration will be large. But the wall is attached to the rest of the building and the ground, making its mass very large. The same force exerted on the massive wall will produce such a small acceleration that it may not even be noticeable. I'll hang one metal ball from this end and place the other metal ball on the platform at the other end. When I release the spring, the first ball will fall straight down, as if it had been dropped from a cliff. And the second ball will be thrown out horizontally. Watch as they hit the table. Did you see them hit at the same time? Let's watch again in slow motion and in a darkened room. The same thing would happen to coins dropped and thrown from a cliff.